The branch circuit overcurrent protection device plays a crucial role in protecting a load from overcurrent conditions. While it is not the only protective device, it is a vital component in ensuring electrical safety. The overcurrent protection device is designed to trip and open a circuit if the current flowing through it exceeds a predetermined level. This prevents the current from reaching a dangerous value that could damage the load or cause a fire. The National Electrical Code, or NEC, provides guidelines and regulations for electrical installations, including overcurrent protection. Several code sections support the role of overcurrent protection devices in protecting loads. NEC Section 210.21b addresses branch circuit protection and states that branch circuits must be protected by overcurrent protective devices in a manner that provides adequate protection from hazards arising from overloads and faults. This means that the overcurrent protection device must be sized and installed to effectively prevent damage to the circuit and the load it serves in the event of an overcurrent. NEC Section 240.4 focuses on the protection of conductors. It specifies that conductors must be protected against overcurrent in accordance with their ampacity, as specified in 310.15. Ampacity refers to the current carrying capacity of a conductor. The overcurrent protection device must be rated to protect the conductor from exceeding its ampacity, which could lead to overheating and potentially a fire. NEC Section 422.11 specifically addresses branch circuit overcurrent protection for appliances. It states that branch circuits must be protected in accordance with 240.4. This reinforces the requirement that overcurrent protection devices are essential for protecting appliances and other loads connected to branch circuits. These code sections collectively establish that the overcurrent protection device is responsible for protecting the conductors and appliances on a branch circuit from overcurrent conditions. While other protective devices, such as thermal cutouts and fuses within appliances, may provide additional protection, the overcurrent protection device remains a primary line of defense against overcurrent hazards. Understanding how overcurrent protection devices work is crucial for electrical safety. An overcurrent condition occurs when the current flowing through a circuit exceeds its rated capacity. This can happen due to various factors, such as short circuits, ground faults, or overloads. A short circuit is an unintended connection between 2 points in a circuit, creating a low resistance path for current to flow. This results in a very high current that can quickly damage equipment and cause a fire. A ground fault occurs when a live conductor comes into contact with a grounded surface, such as a metal enclosure. This creates a path for current to flow to ground, which can also result in a high current and potential hazards. An overload occurs when a circuit is subjected to a current that exceeds its rated capacity. This can happen if too many appliances are connected to a single circuit or if an appliance draws more current than it is designed for. Overcurrent protection devices are designed to detect these overcurrent conditions and quickly interrupt the flow of current, preventing damage to the circuit and the load. There are two main types of overcurrent protection devices: fuses and circuit breakers. A fuse is a one-time use device that contains a thin strip of metal that melts and breaks the circuit when the current exceeds its rated value. Once a fuse blows, it must be replaced with a new one. A circuit breaker is a reusable device that uses a mechanical mechanism to trip and open the circuit when the current exceeds its rated value. Unlike fuses, circuit breakers can be reset or reused after they trip. Both fuses and circuit breakers are rated in amps, which indicates the amount of current they can carry before tripping. The amp rating of an overcurrent protection device must be carefully selected to protect the circuit and the load it serves. If the amp rating is too low, the device may trip unnecessarily, interrupting the flow of power. If the amp rating is too high, the device may not trip quickly enough to protect the circuit and the load from damage. The National Electrical Code provides guidelines for selecting the appropriate amp rating for overcurrent protection devices based on the size of the conductors and the type of load being served. The code also specifies the types of overcurrent protection devices that are permitted for different applications. In addition to protecting against overcurrent conditions, overcurrent protection devices also provide protection against short circuits and ground faults. These types of faults can create very high currents that can quickly damage equipment and cause a fire. Overcurrent protection devices are designed to trip quickly in response to these high currents, preventing or minimizing damage. It is important to understand that overcurrent protection devices are not designed to protect against voltage surges or other types of electrical disturbances. Voltage surges can damage sensitive electronic equipment, and surge protection devices are specifically designed to protect against these types of disturbances. Surge protection devices are typically installed at the service entrance of a building or at individual outlets to protect sensitive electronic equipment. In summary, the branch circuit overcurrent protection device plays a critical role in protecting the load from overcurrent conditions. The National Electrical Code requires that branch circuits be protected by overcurrent protection devices in a manner that provides adequate protection from hazards arising from overloads and faults. Overcurrent protection devices are designed to trip and open the circuit when the current exceeds its rated value, preventing damage to the circuit and the load. It is important to select the appropriate amp rating for overcurrent protection devices and to install them in accordance with the National Electrical Code. While other protective devices may provide additional protection, the overcurrent protection device remains a primary line of defense against overcurrent hazards. Therefore, it is incorrect to state that the branch circuit overcurrent protection device does not protect the load. In fact, it plays a critical role in protecting the load and ensuring the safe operation of the electrical system. Now let's delve further into the specifics of how overcurrent protection devices function and are applied within electrical systems. We will examine the different types of overcurrent protection devices, their characteristics, and the factors that influence their selection and application. We'll begin with fuses, which are among the oldest and simplest types of overcurrent protection. A fuse consists of a metal strip or wire, designed to melt and interrupt the circuit when the current exceeds a specified level. The fuse element is typically enclosed within a non-combustible housing, often made of glass, ceramic, or fiberglass. Fuses are characterized by their amp rating, which indicates the maximum current they can carry without melting, and their voltage rating, which specifies the maximum voltage the fuse can safely interrupt. Fuses are also categorized by their interrupting rating, which indicates the maximum fault current they can safely interrupt without rupturing or causing a fire. Fuses are available in a wide range of amp ratings from fractions of an amp to thousands of amps, and voltage ratings from a few volts to thousands of volts. They are also available in different time delay characteristics, which determine how quickly they respond to overcurrents. Some fuses are designed to trip very quickly, while others are designed to allow brief overcurrents to pass without tripping. This time delay characteristic is important for protecting circuits that may experience temporary overcurrents, such as those caused by motor starting. There are several types of fuses, each designed for specific applications. Cartridge fuses are commonly used in residential and commercial applications. Plug fuses are typically used in older residential electrical systems. Blade fuses are commonly used in automotive applications. Semiconductor fuses are designed to protect sensitive electronic components. Now let's move on to circuit breakers, which are electromechanical devices that automatically interrupt the circuit when an overcurrent is detected. Unlike fuses, circuit breakers can be reset and reused after they trip. Circuit breakers consist of a bimetallic strip or an electromagnet that responds to overcurrent. When an overcurrent occurs, the bimetallic strip bends while the electromagnet trips a mechanical latch, which opens the circuit. Circuit breakers are characterized by their amp rating, voltage rating, and interrupting rating, similar to fuses. They are also characterized by the trip curve, which indicates how quickly they respond to different levels of overcurrent. Circuit breakers are available in a wide range of amp ratings, voltage ratings, and trip curves. They are also available in different types, such as thermomagnetic circuit breakers, which use both a bimetallic strip and an electromagnet to trip, and electronic trip circuit breakers, which use electronic sensors and microprocessors to detect overcurrents and trip the breaker. There are several types of circuit breakers, each designed for specific applications. Standard circuit breakers are commonly used in residential and commercial applications. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults, which can be particularly dangerous. Arc fault circuit interrupters, or FCIs, are designed to protect against arc faults, which can cause fires. Molded K-circuit breakers are used in industrial and commercial applications. Insulated K-circuit breakers are used in high-voltage applications. The selection of an overcurrent protection device depends on several factors, including the ampacity of the conductors being protected, the type of load being served, the interrupting rating required, and the application environment. The ampacity of the conductors must be considered when selecting the amp rating of the overcurrent protection device. The overcurrent protection device must be rated to protect the conductors from exceeding their ampacity, which could lead to overheating and potentially a fire. The type of load being served also influences the selection of the overcurrent protection device. Some loads, such as motors, may require time delay fuses or circuit breakers to allow for brief overcurrents during starting. Other loads, such as sensitive electronic equipment, may require fast-acting fuses or circuit breakers to protect against voltage surges. The interrupting rating of the overcurrent protection device must be sufficient to safely interrupt the maximum fault current that could occur at the point of installation. The interrupting rating is typically determined by a short-circuit study, which analyzes the potential fault currents in the electrical system. The application environment can also influence the selection of the overcurrent protection device. For example, in damp or corrosive environments, special fuses or circuit breakers may be required to protect against corrosion. The National Electrical Code provides detailed guidelines for selecting and installing overcurrent protection devices. The code specifies the types of overcurrent protection devices that are permitted for different applications and provides tables and formulas for calculating the appropriate amp ratings and interrupting ratings. It is essential to follow the National Electrical Code when selecting and installing overcurrent protection devices to ensure the safety and reliability of the electrical system. In addition to selecting the appropriate overcurrent protection device, it is also important to properly install and maintain it. Overcurrent protection devices should be installed in readily accessible locations and should be clearly labeled to indicate their amp rating and function. Overcurrent protection devices should be periodically inspected to ensure that they are in good working condition and that they have not been damaged or tampered with. Fuses should be replaced immediately after they blow, and circuit breakers should be reset promptly after they trip. It is also important to keep spare fuses and circuit breakers on hand for emergencies. In conclusion, overcurrent protection devices are essential components of electrical systems that protect against overcurrents, short circuits, and ground faults. The branch circuit overcurrent protection device plays a critical role in protecting the load from overcurrent conditions, ensuring the safe and reliable operation of the electrical system. It is therefore incorrect to state that the branch circuit overcurrent protection device does not protect the load. In fact, the overcurrent protection device is a primary line of defense against electrical hazards. The National Electrical Code provides detailed guidelines for selecting, installing, and maintaining overcurrent protection devices. By following these guidelines, it is possible to ensure that electrical systems are properly protected and that the risk of electrical hazards is minimized. To further clarify the role of overcurrent protection, let's consider some specific examples. Firstly, imagine a scenario where a homeowner plugs too many appliances into a single circuit. This could easily overload the circuit, causing the current to exceed the ampacity of the conductors. If the circuit is properly protected by an overcurrent protection device, such as a circuit breaker, the breaker will trip and interrupt the flow of current, preventing the conductors from overheating and potentially causing a fire. Secondly, consider a situation where a short circuit occurs in an appliance, such as a toaster. A short circuit creates a low resistance path for current to flow, resulting in a very high current that can quickly damage the appliance and the wiring in the circuit. If the circuit is protected by an overcurrent protection device, the device will trip quickly in response to the high current, preventing or minimizing damage. Thirdly, imagine a scenario where a ground fault occurs in an electrical outlet. A ground fault occurs when a live conductor comes into contact with a grounded surface, such as the metal enclosure of the outlet. This creates a path for current to flow to ground, which can be dangerous. If the circuit is protected by a ground fault circuit interrupter, or GFCI, the GFCI will detect the ground fault and quickly interrupt the flow of current, preventing electrical shock. These examples illustrate the importance of overcurrent protection devices in protecting against various types of electrical hazards. Without overcurrent protection, these hazards could lead to serious injuries, property damage, and even fatalities. It is also important to note that overcurrent protection devices are not foolproof. They are designed to protect against overcurrents, short circuits, and ground faults, but they may not protect against all types of electrical disturbances. For example, overcurrent protection devices are not designed to protect against voltage surges, which can damage sensitive electronic equipment. Surge protection devices are specifically designed to protect against voltage surges. Furthermore, overcurrent protection devices can fail or malfunction, which could compromise their ability to protect against electrical hazards. It is therefore important to periodically inspect and test overcurrent protection devices to ensure that they are in good working condition. If an overcurrent protection device fails, it should be replaced immediately. In addition to providing overcurrent protection devices can also help to improve the reliability of electrical systems. By preventing overcurrents, short circuits, and ground faults, overcurrent protection devices can help to extend the life of electrical equipment and reduce the risk of downtime. Overcurrent protection devices can also help to reduce energy consumption by preventing unnecessary power losses due to overcurrents. In conclusion, the branch circuit overcurrent protection device is an essential component of electrical systems that plays a critical role in protecting the load from overcurrent conditions. The National Electrical Code requires that branch circuits be protected by overcurrent protection devices in a manner that provides adequate protection from hazards arising from overloads and faults. Overcurrent protection devices are designed to trip and open the circuit when the current exceeds its rated value, preventing damage to the circuit and the load. It is important to select the appropriate amp rating for overcurrent protection devices and to install them in accordance with the National Electrical Code. While other protective devices may provide additional protection, the overcurrent protection device remains a primary line of defense against overcurrent hazards. Therefore, it is incorrect to state that the branch circuit overcurrent protection device does not protect the load. In fact, it plays a critical role in protecting the load and ensuring the safe operation of the electrical system. Let's expand on the discussion by examining the practical aspects of selecting and installing overcurrent protection devices in various scenarios. Consider a residential setting. The National Electrical Code specifies the minimum ampacity requirements for branch circuits serving different types of loads. For example, a general-purpose branch circuit serving lighting and receptacles must have an ampacity of at least 15 amps. A small appliance branch circuit serving kitchen counter receptacles must have an ampacity of at least 20 amps. A dedicated branch circuit serving a large appliance, such as a refrigerator or an air conditioner, must have an ampacity sufficient to handle the appliance's load. The overcurrent protection device for each branch circuit must be selected to protect the conductors from exceeding their ampacity. For example, a 15-amp branch circuit should be protected by a 15-amp circuit breaker or fuse. A 20-amp branch circuit should be protected by a 20-amp circuit breaker or fuse. It is important to note that the overcurrent protection device should not be sized larger than the ampacity of the conductors. This could allow the conductors to overheat and potentially cause a fire. In addition to the ampacity requirements, the National Electrical Code also specifies the types of overcurrent protection devices that are permitted for different applications. For example, arc fault circuit interrupters, or RFCIs, are required for branch circuits serving bedrooms in new residential construction. RFCIs are designed to protect against arc faults, which can cause fires. Ground fault circuit interrupters, or GFCIs, are required for branch circuits serving bathrooms, kitchens, and outdoor receptacles. GFCIs are designed to protect against ground faults, which can cause electrical shock. Now let's consider a commercial setting. Commercial electrical systems are typically more complex than residential systems and require a higher level of overcurrent protection. Commercial buildings often have multiple branch circuits serving a variety of loads, including lighting, receptacles, appliances, and equipment. The overcurrent protection devices for commercial branch circuits must be selected to protect the conductors from exceeding their ampacity and to provide adequate protection against overcurrents, short circuits, and ground faults. In addition to the ampacity and protection requirements, commercial overcurrent protection devices must also meet certain performance standards. For example, commercial circuit breakers must have a certain interrupting rating, which indicates the maximum fault current they can safely interrupt. The interrupting rating must be sufficient to handle the potential fault currents in the commercial electrical system. Commercial overcurrent protection devices must also be properly labeled and maintained. The labels must indicate the amp rating, voltage rating, and interrupting rating of the device. The devices must be periodically inspected and tested to ensure that they are in good working condition. Finally, let's consider an industrial setting. Industrial electrical systems are typically the most complex and require the highest level of overcurrent protection. Industrial facilities often have large electrical loads, such as motors, pumps, and machinery. The overcurrent protection devices for industrial branch circuits must be selected to protect the conductors from exceeding their ampacity and to provide adequate protection against overcurrents, short circuits, and ground faults. In addition to the ampacity and protection requirements, industrial overcurrent protection devices must also meet stringent performance standards. For example, industrial circuit breakers must have a high interrupting rating and a fast tripping speed. The interrupting rating must be sufficient to handle the high fault currents that can occur in industrial electrical systems. The tripping speed must be fast enough to protect sensitive equipment from damage. Industrial overcurrent protection devices must also be designed to withstand harsh environmental conditions such as high temperatures, humidity, and dust. The devices must be properly installed and maintained to ensure their reliable operation. In conclusion, the selection and installation of overcurrent protection devices depend on the specific application and the type of electrical system being protected. The National Electrical Code provides detailed guidelines for selecting and installing overcurrent protection devices in various settings. By following these guidelines, it is possible to ensure that electrical systems are properly protected and that the risk of electrical hazards is minimized. Overcurrent protection is not just about preventing fires or electrical shocks, it's about ensuring the reliable and efficient operation of electrical systems. By properly protecting circuits from overcurrents, we can extend the life of electrical equipment, reduce downtime, and improve energy efficiency.